And we are live, everybody. Good to see you. Thank you for joining. Glad you could all make it. Just want to say thank you to all the YouTube channel members for making this show possible. Thank you for all your support. All my Patreon members, you guys are awesome. And just everybody that supports me financially through PayPal and through any means necessary with super chats and super stickers. Thank you all for that. Thank you, Michael Kahn, for coming. Weiskopf, YouTube, Lumpy Gas in a Vacuum. Who else is here? And that seems like everybody in the chat because it is a members only evening. So yeah, if you guys want to be part of the members only evenings, which is usually between a Thursday and a Friday evening a week, please do become a member. Yes. So thank you guys. I hope you guys are all doing well today. Hey Michael, thank you for coming and being in the panel. How are you doing today, sir?
I'm doing fine.
Oh, that's good. Are you breathing gas?
I'm definitely breathing gas.
And would that be pressure?
It would definitely be pressure.
And would you be able to breathe this gas pressure if you didn't have lungs?
No.
Would that lungs be a container?
Yep.
Yeah. Simple stuff. Funny thing is, guys, we can demonstrate gas pressure requires containment over and over with different demonstrations. Heck, even the globe guys that bring their so-called demonstrations bring it in containment and then measure it with containment, going totally against their own argument. Yes, container is the antecedent for gas pressure. Very simple stuff. Otherwise, we would not be able to breathe. So we do have a poll going on at the moment. It is 13 votes. Gas requires containment to cause gas pressure. So yes, 71%, no, 29%, 14 votes. It's good to see that the majority of the people understand how thermodynamic systems work and gas behavior, because you have that V, which means volume, means it's got containment, guys. You cannot have a volume without a barrier, without containment to have a volume, because you got substance to hold it into. Now you can create an arbitrary volume inside a system, but that is just a arbitrary volume inside a originally based system. This is why we get, when we get like Mr. Sensible going up in the Burj Khalifa and saying, oh look, at ground level there's more gas pressure than when I went up. Little does he know that that whole building is inside the whole system that has already got the pressure gradients. And when you say gas pressure, you are already conceding gas pressure, so gas behavior. Hey Two Wolves, good to see you. Thank you for joining us. No, gravity cannot do anything to gas. If you don't believe me, can you see my screen, Michael? I'm sure you can. Okay, listen up.
Hi, I'm Emerald Robinson, and in this What Is video, we're going to investigate the state of matter called a gas. Gases are materials that have no definite volume and no specific shape.
Yeah, remember, we're going to stop at every point. No definite volume, no specific shape. Why is that? Because gas takes the shape of its container. So when you say atmosphere, it's like Nathan likes to say, oxymoron, because gas has no shape. This is gas behavior 101. So the only shape it can take is to its container, because it's bouncing around at that barrier constantly.
In other words, gases can easily flow into and take the shape of a container and will expand, redistributing themselves to evenly fill that container.
Okay, so take the shape of a container, so it can go in and out to take the shape of the container, guys. That would be if it's an open system, that is.
Although there are many types of gases, there are a few characteristics that they have in common. First, particles in a gas have no real arrangement. They can move over and...
So no real arrangement, guys. So that means they're all mixed together all over. You know, like Dalton's law, it's a conglomerate of gas. It moves in all directions. They have their different densities, and they are always bumping into each other and moving all around. So therefore you can have pressure gradients. Hence why we live in a dynamic closed system, because the sun heats up and it gets cold and we have wind blowing, and you got so much different things, condensation. We got what we call a dynamic system, which has cycles. Those cycles create why we have the pressure gradients. Obviously we have higher pressure gradient on the bottom because there's more things to hit off of, more surfaces. The higher you go up, the less heat, it gets colder, and the more area to spread out. And because there's already less gas up there, you have less pressure. Interesting fact though, you have to use a container to measure that pressure, aka like a barometer. Hey Jess Palmer, good to see you. Thank you for coming. Alan Norstrand, thank you for coming. Yeah, it's good to see you guys.
Past one another, and the space between the molecules can increase or decrease. Molecules in a gas collide with one another and move more quickly or more slowly based on factors like temperature and pressure, but they will always spread out fairly equally to fill.
Yep, PVNRT. Yeah, ideal gas law, guys. Although it's just a gas law to explain it more, in broader terms. It's just in ideal circumstances, but these relationships still hold true no matter the system. It means this is still a true law.
The space that they're in. All of this molecular movement means that gases hold a lot of kinetic energy.
Yeah, so remember, it fills the space, aka fills the still shows offline.
The last thing I can see on YouTube.
Yeah, okay, now it's streaming again, guys. Okay, we're gonna have to send a new link to everybody. Hey everybody, I'm live again. Some odd reason it just decided to kick me off. So yeah, if you want to watch what you just missed, you'll have to go to the first stream we just had. This is now the new stream. Sorry all for this idiotic. Oh, are we on the same stream?
I don't know.
It looks like it.
My YouTube's just not working.
I think we're on the same stream, yeah. Okay, that's great news. Sorry about that, guys. It just, OBS decided to change my settings while we were streaming. Or actually, YouTube didn't want me to stream. I don't know, something like that. But it's good to be back. If you guys are ready, then we can carry on what we were doing. Oh, sorry about that. That's not what I wanted to do.
Just carry on. I can't see YouTube at all now.
Okay, same stream. So, yeah, where I was, it fills the space. Okay, I see there's some more people that are voting. 36 votes. Gas requires containment for gas to cause pressure. 52% yes, no 48%. It definitely needs it, guys. But let's carry on. Hey, Spuddy, good to see you. Thank you for coming. Sorry, guys, for this. Whatever just happened, I do apologize.
To one another. Third, gases can flow from one area to another, although the direction of flow is not directly affected by gravity.
Oh, did you guys hear that? Let's listen back to that.
Because there is space between the molecules in a gas, it can be placed under pressure and squeezed so that the particles are forced to be close to one another. Third, gases can flow from one area to another, although the direction of flow is not directly affected by gravity.
Oh, did the ballers listen to that? Because every time we get, oh, gravity, 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 gravity. Let's listen again.
Third, gases can flow from...
Sorry?
I say gravity is the container.
Yeah, no, it's not. Listen to what they say.
It's not.
Yeah, but listen what
one area
that's what she's saying.
Another, although the direction of flow is not directly affected by gravity.
Although the direction of flow is not directly affected by gravity. So gravity cannot contain gas. Gravity cannot tell gas which way to go. It cannot direct it. First of all, gravity is not a force. Secondly, gravity does not exist. And even if it was a force, it would still be too weak to do anything. So yeah, ballers, just listen a bit, one more time, come on.
This can flow from one area to another, although the direction of flow is not directly affected by gravity. This ability to flow means they are sometimes referred to as fluids. Last, gases have melting points and boiling points that are below room temperature. For the most part, we are unable to see gases because of the space between their particles. Scientists have to use characteristics like pressure,
Scientists have to use characteristics like pressure. And how do they use that pressure, guys?
volume, number of particles per unit area.
Yeah, volume, number of particles per unit area. Very weird. You know, in containment.
And temperature to discuss and identify them. Gases are commonly used in things like cooking, healthcare, and scientific research, and they even make up the air we breathe.
Gases make our atmo. So yes, we breathe gas, guys. Even water has to be contained. Exactly, Jeff. Good to see you. Thanks for coming. Okay, so that was very simple to show. Then we got another one. Oh, this is the good one. Hey, Skeptic 936, good to see you. Glad you could make it. Yeah, PSI for a reason, Spuddy. Pounds per square inch. You guys obviously know this video, but this is the full one. I think there's some parts that we actually want to go through it.
It's been quoted as the sine qua non of scientific enlightenment, rather as Shakespeare and Beethoven might be quoted to represent the arts. Whilst the position of Shakespeare and Beethoven in our common...
Okay, we don't need to know. He's going to be talking about thermodynamics, guys.
And yet, it's an idea of great significance and beauty, and one which affects every aspect of our lives. It's true that some specialized knowledge is required, perhaps a little mathematics, to interpret the law fully. But a specialized training is necessary to interpret Beethoven fully. The real question to us is, can we understand the law well enough to derive pleasure and satisfaction from it?
Spuddy, exactly. Force applied to the inside walls of the container. Exactly, that's what it is. Remember, when I say may the pressure be with you, it means the gas pressing against the container walls. Without the pressure, there can be no air we breathe. So you require the container to have the pressure. So that's why I say may the pressure be with you, because it's literally the force on the container.
And I hope that you will agree with me that this is possible. In fact, the essential idea of the law has already been stated. It isn't a difficult idea. It's the idea of increasing disorder. That the randomness, chaos, disorder of the universe is always increasing.
Yep, always increasing. So if you're going to have it in another system, it's always going to increase. The disorder increases, aka entropy, guys. So if you have an open system, like this cup, for instance, it's an open system. There's gas pressure inside this cup. Now, let's say it's closed. Now, what happens when I open it? I open it, the gas is moving all around, so it's going to go into the surrounding system. And the gas that's there is going to go. So it's going to equalize around. So all the gas is going to go and have more disorder. Just more microstates. You could say possible microstates, because you've increased the volume of the now increased system. So like if Earth is an open system, inside the universe as the low pressure system, Earth cannot exist with gas pressure, because it would all equalize into space. Therefore, we would not be able to breathe. We would be 10 to the minus 17 tall here at ground level, because the gas would escape instantaneously, guys. Get it? The reason we do not have instantaneous away is because we have pressure gradients in a dynamic system, and it's closed. So yeah.
Now, full statement of the law can be made in many ways, and to some extent it's a matter
Hey
of
Kevlar, good to see you. Thank you for coming.
Just so as to treat the subject fairly, I shall state it in at least 4 ways. But the one I prefer is the first one, which I've written on the board as neatly as I can.
I like the way they've written this. Drew, listen carefully, Globe guys.
Every system, if left to itself, will, on the average, change towards a condition of maximum probability. That's a full statement of the second law. One or two things about it are worth noting. First of all, the word system. This is just the thing we're interested in, the machine, the substance. Whatever we happen to be interested in, we call the system. Probability. We talked about that. Probability is just a measured as the number of ways in which the system, which we've defined, can arise. And finally, the words on the average, which don't appear in all statements of the second law, but should, because the law is a statistical law.
Yep, it's a statistical law because that's how they describe it. That's why. It's based on physical function though, so that's why it's a statistical law, because if it didn't have the physical function, you wouldn't be able to have the statistics to describe it. That's why it has the probability function, guys.
The earlier statements didn't deal with it as a statistical law. It is statistical, and deviations from the second law of thermodynamics are possible. It's only true on the average. The Brownian motion, which we saw, shows every time the little Brownian particle moves a departure from the second law. But on the average, the second law is obeyed.
You understand that, guys? The Brownian motion, it's on the average it's obeyed. So just because every single particle is moving doesn't mean it's not obeying the full thermodynamic law. That's why it's the system as a whole. So that's why when we have the system, Earth as a closed system, it has pressure gradients. Understand? Because it is still abiding to the thermodynamic law, because it's at average. So remember, ground level, you have more for the gas to hit off of, so therefore higher pressure. The sun is able to heat up the ground more, so it's able to heat the gases up more, therefore it can move faster. And then it gets colder, and we have cycles. And the higher you go up, the more open area there is for that gas to move around. Now eventually, when you do get high enough, like let's say past Mount Everest or whatever, most of the gas is still down at the bottom, so that gas that is still there is moving around. Now if it's starting to heat up at that point, it's just going to move faster. It's not going to create more gas, it just literally creates the gas to move faster when you heat it up. So pressure gradients in a dynamic closed system.
It's a statistical law. Now we saw how entropy was related to probability by the equation S equals K log P. And therefore, if the probability is going to a max...
Yes, exactly, Jess Bomb. I don't know if you guys have done this before. You can go to, let's say you go fishing, and you're there at the dam, and you can take a pressure reading, and then you go and take the same pressure reading when the sun has gone down. You get a different pressure reading because the gas is now moving at a slower rate because it's colder. You're still at exactly the same spot. The pressure differential is just a little bit different because the gases are not moving as fast, but you still got the same amount of gas there.
Maximum, as it does in the statement which I've just written, so the entropy should follow it. And so a second statement which we can use is the one I've written here. In any spontaneous process, the total entropy increases.
That word, guys, spontaneous. Remember that word. Spontaneous process, guys. That's what would happen. A spontaneous process if the Earth was an open system inside space as the so-called vacuum. It would be a spontaneous process, not a, how can you put it, pressure gradient process. it's not structural, it would be spontaneous. The total entropy increases because more microstates are available to the system because it has increased.
That follows from the S equals K log P. Now the word total here is very important. We must remember to include everything which takes part in the change, otherwise we shall get our sums wrong. If necessary, the whole universe, anything involved in the change. In fact, this inclusion of the whole universe is quite a good way to do it, and Clausius very succinctly expressed both the first and second laws of thermodynamics with the words: Die Energie der Welt ist konstant, die Entropie strebt einem Maximum zu. The energy of the world is constant, the entropy tends to a maximum.
Do you guys understand that? The energy of the universe is constant, the entropy is to a maximum. So it's always expanding to the maximum. So it's trying to equalize. So as soon as you present it with a new further open space to occupy with gas, it will occupy the system. Because remember, the gas has kinetic energy. It's always bouncing into each other and bouncing off in every which way direction. So it's going to always move. Gas never stops moving. No matter if you got a gravity belief, it doesn't stop moving. Gravity has no direction on the gravity has no effect on the direction of gas. Hey Rachie, good to see you. Thank you for coming. I don't think entropy always increases. They only say that because of the Big Bang, I believe. As for the tea evaporating, I've had a cup of water in my fridge before and still evaporated. What? And it still evaporated, disappeared. Yes, it will evaporate eventually, but it does always increase, Rachie, because look at it this way. If you got a system and you got a system around it, if that is now just gas, it's closed, it's moving, but the system around it is just the system around it, it's the boundary. But you got another system with its boundary. Now the gases are moving there. It's always moving. It's got the possibility to be able to, if you do open the system, to increase into that surrounding system. So just because it's not open doesn't mean it doesn't have the possibility. So now we open the system, now it has increased because it is now going into that open system. It has created a new maximum. It has expanded, and therefore the microstates has more chaos. It has more probability. That's why.
Now, I can express that statement mathematically very simply indeed. This, if you like, is a third way or fourth way of expressing now both laws of thermodynamics. First of all, the first law says that the increase in energy of the universe equals naught. There's the first law of thermodynamics, and the second law says that the increase in entropy of the universe is equal to or greater than naught. We said that the entropy of the universe is always increasing. That means it's greater than naught. Well, it can be just greater than naught. It can be equal to naught.
Remember, energy cannot be created or destroyed, hence naught. It can only be transformed or transferred, hence thermodynamics. Greater or the same as naught.
Mustn't decrease. So those are two ways of expressing the first and second laws. We shall meet others. The second law is a strange law. Nothing is conserved, nothing adds up. Most laws of science are concerned with the conservation of something, the conservation of mass, the conservation of energy, or something like this.
Hey Anamika, good to see you. Thank you for coming. Yes, Weiskopf, simple stuff, guys. I really hope you are paying attention, Weiskopf, because every thing he's explaining goes against the globe model. So, yeah. I can't believe we've already gone through 23 minutes. It's good to see you, Adam Eakin. Thank you for joining.
Law just doesn't add up. It says something increases.
Hi, Fatish first. Good to see
But
you.
we shall find that it's a quantitative, useful law, nevertheless. Whilst we're at it, I might refer to the other law of thermodynamics, the third law, because it's quite quickly disposed of, for the moment anyway. The third law is one which deals with the absolute value of the disorder, or entropy. The third law says that the entropy of a perfectly crystalline substance,
Hi,
perfectly
Gwenda,
ordered crystalline
97,
substance, at
welcome.
the absolute zero may be taken as zero.
And do we ever get anything at absolute zero? Does gas ever go to absolute zero, guys? Do we get a gas going to minus 270 degrees Kelvin? No, we do not. So therefore, the gas would still always have kinetic energy moving in the direction. So let's put it this way. If the gas had moved, bounced off the ground, and it is moving upwards in that direction, if it's not going to hit anything, it will not ever return back, because it will always have kinetic energy. Gas always has kinetic energy. It can only change direction if it has hit into another anything. So yes, thank you, Fashalti. Thank you for your $2 super chat. Really do appreciate it. You really do support this channel a lot with your super chats. I really appreciate it. Thank you. Yeah, I'm looking at maybe buying some lighting equipment on the Black Friday thing tonight and take a lot. So yeah, that will be me 12 o'clock tonight. Gases fill the available space in a vacuum. Exactly. That's why nature abhors a vacuum, because there is always gas present, because it literally moves to the lower pressure. That's entropy, guys. Crystalline solid at minus 273 Kelvin. Exactly. Adam Meekin. That's why, where do we see that? Let's see. Weisskopf. No, because gravitational waves exist and moves gases from all around our solar system. It's a near perfect vacuum though. No, Weisskopf. Can you please provide us with evidence for that very idiotic claim? There is no such thing as gravitational waves. You first have to observe them, and then you have to go and demonstrate them for us, please.
And if we want to write it, we can write it as S at the absolute zero equals 0. But I'll dot that round, because you must remember that that is has the restrictions which I mentioned in the full sentence, which I just spoke. Well, there are the three laws.
No, gas as we experience it would be gas at minus 273, but minus 273 is theoretical. Exactly, that's why the Kelvin scale, their zero is minus 273 Kelvin. It is theoretical because it can never be observed.
Of thermodynamics, very simply expressed. Now let us look at some examples.
Exactly, madam.
Of
Would not.
spontaneous changes, and see how they are accounted for in terms of the second law of thermodynamics. We'll take the simplest first and look at changes where...
Yes, Rachel's correct. Weisskopf, Cavendish, first of all, is not an experiment, and he was trying to measure the density of Earth. Absolutely nothing to do with thermodynamics. Absolutely nothing to do with gravitational waves. Get it? All it was torsion twist. That is what he measured, and they took those oscillations of the torsion twist and made a deduction saying, I correlate Earth's density to be this much based on that. Simple as that. And no, you should be able to actually provide it to us. The idea of gravitational waves describe Einstein's space and perspective nicely. Just because it describes your beloved Einsteinian fourth dimension, I might add, theory that is not actually scientific, does not make it real, Weisskopf. Please demonstrate it for us. That's what I asked.
Only the entropy changes. Now, one, perhaps the simplest of all, of these is the expansion of a gas into a vacuum.
Okay, now you must pay attention, Glovers, especially you, Wisecoff. Pay attention.
I have in one of these bulbs some bromine, and in the other I have a vacuum.
Okay, guys, remember, in containment, bromine, in containment, a vacuum. It is literally just cut off there by a valve. Now, why would he need to actually have these containers here to demonstrate this if he didn't need it, if gravity could do it for him? Oh wait, because gravity can't do it. Gravity is not a force. Gravity doesn't exist. So let's watch what happens and listen to the words, Wisecoff. Listen.
And if I open the tap between these two, you will see spontaneously the bromine rush from one to the other.
Okay, first one. Spontaneously rush from one system to the other. Understand? High pressure to low pressure. Do you see how it's equalizing these two systems? It has increased the microstates. That's all. It has now increased the probability of more microstates. That's it. So if he had to break these vials open now, it would spread into the next surrounding system, hence the system he is standing in, which we are all standing in.
Now that is the simplest change we can have, perhaps, because all that happens is a change in entropy.
All that happens is a change in entropy. Listen to these very, 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 very specific words next, guys.
In this case, the expansion into a vacuum, nothing else is involved. There's no energy change, there's no temperature change, there's no change except entropy.
There we go. That debunks your whole gravity argument presented by Professor Full and gravity pulls it down and therefore it releases it stops the kinetic energy so it cannot reach space. This is why gravity cannot be a container, guys, because nothing changes except entropy. The energy does not change. Let's listen to that again, guys. This is why it's so death-defying to you guys.
The bromine rush from one to the other. Now that is the simplest change we can have, perhaps, because all that happens is a change in entropy. In this case, the expansion into a vacuum, nothing else is involved. There's no energy change, there's no temperature change, there's no change except entropy.
No change except entropy. Yes, face reality. Why can't globies comprehend this simple demonstration? Exactly. It's in their face. Just this statement alone, this demonstration alone debunks the argument that gravity is the container. Full stop. It's as simple as that.
It's pure denial.
Exactly. I mean, think about it. What is their argument why gravity is a container? Because they say it holds the it pulls it down. It causes it not to have enough kinetic energy to leave Earth. That's why. But this goes against it. There's no change in energy. There's no change at all. Temperature, nothing. The only change is entropy. And entropy is the statistical matter of it increasing into the surrounding system because it changes the probability of the microstates. Simple. Your globe has just been debunked, guys. There's no such thing as gravity being a container. We would all be dead if it was. Because entropy would simply laugh at gravity if it was like that. So Michael, what do you have to say about this?
Very little. I mean, we're just going around in circles, aren't we, again?
Yeah, I mean,
Yeah.
they ignore the word spontaneous. They ignore the word no energy, no temperature change. It's literally just entropy. That's it.
We're getting people parroting gravity as a container, but we're not seeing no scientific evidence for gravity in first instance. So
Yeah, where's the demonstrations for it? So, if anybody watches this and says you don't need containment to have gas pressure, then they are literally in denial. Literally. They are being dishonest with themselves and dishonest to everybody they communicate with about gas pressure. I mean, I've shown a video so far where a woman literally says gravity has no effect on the direction of gas. Then we have him literally showing us and explaining no energy change, no temperature change, just entropy. That's it. Heck, we even have Conspiracy Cat stating, without the container, there can be no pressure. Thank you, Conspiracy Cats, 2019. Without the balloon, there can be no pressure. Is Lumpy in as well? How's it, Lumpy?
Yeah, I'm in.
You have anything to say about this? Hey, Alan, good to see you.
Yeah. A downward bias is that claim, that idea, that concept is a refutation of gas behavior. It moves in all conceivable directions. It doesn't have any bias down.
Exactly. They can't show us gas just staying stagnant, can they? I mean, even if they have
any bias in direction at all.
Yeah.
It moves. It presses against every barrier it has equally.
Yeah.
In all demonstrations.
Exactly.
So to have any kind of a downward bias is ridiculous, because it refutes basic gas behavior. Like, go back to like the first time we ever were introduced to it in a textbook.
Yeah.
And it says it points it going every direction, not any down. There's no down.
That's why I love when they bring their so-called. I think they're clever by bringing butane or a very dense gas in a fish tank, and then they float the boat there. But why do they keep that fish tank closed when they're finished? Because it disperses into the surrounding system. It just takes longer, hence the arrow of time, because it's denser. It literally takes longer for it to bounce out of the system. That's all. Doesn't matter how dense the gas is, it will always disperse into the surrounding system. Always. Because the energy stays the same. There's no change in energy. Do they understand that? The only thing that happens is if the gas is getting hotter, it jiggles around a bit faster. That's about it. But it does not change the energy when it happens in the entropy change. That's all. When it happens spontaneously, yeah, they ignore the word spontaneous. Now they think, oh, we got pressure gradients, so therefore entropy is not happening. You guys are all talking rubbish because it would equalize in the system. No, that's just, again, a misunderstanding of how thermodynamics works, because the reason we have pressure gradients is because we're in a dynamic closed system. We wouldn't have pressure gradients if it was an open system, because it would literally disperse into the surrounding system, because it is a low pressure system.
It's a billion times 100 million to get to the 17th exponent, and that's a ridiculous number.
Yeah, I still don't know how people can watch this and listen to this and still fight for gravity as a container.
Why are people still saying it's a farce? I mean, I'm seeing things like it pulling and pushing, and it don't do none of them things because it's not a farce and it's not even real to start with.
Yeah, didn't they watch my video the other night where I literally show someone saying there is no gravity on the surface of Earth, and this is based on general relativity. Literally, there's no gravity.
These ballers don't know their own model.
They don't. They do not understand their model. And they still think somehow Newtonian and Einsteinian are the same thing. It's beyond idiotic.
The entropy concept, that would have been difficult to understand and difficult to account for.
Okay, I think that was quite good. I think let's go and look at some more videos. I've got some astronaut videos, guys. Exciting. Just trying to look for it quickly. Downloads. There we go. I want to show the one where the guy goes in there and he literally. I got Neil Armstrong in a vacuum as well, guys.
But the ultimate and most dangerous test was a huge, specially constructed vacuum chamber.
Whoa. Huge,
Whoa.
specially constructed vacuum chamber, guys.
Is that another container?
Yeah, look, container in a container in a container. Because you know why? Because they cannot even get close to a replicatable so-called space with a vacuum. And because it would literally crush itself. Because pressure, you know, the pressure is a force. It's the force exerted on the surface area. Gravity is not a force.
They were able to pull all the air out to create a big vacuum, just like it would be on the moon.
No, not like on the moon, because you're not going to get even close to what the so-called pressure is said to be on the moon. So that's a lie, but okay.
That way we could test our suits to make sure there was no leakage.
Oh. Suits, no leakage. Well, if you think about it, they got zips. Is zips airtight, guys? As far as I know, a zip is not airtight. And they got zips on the astronauts' clothing, you know, on their spacesuits.
One such test narrowly avoided disaster. Jim LeBlanc was the test subject in the vacuum chamber. Cliff Hess, the supervising engineer outside.
Yeah. Remember, he was the guy that almost died in the vacuum chamber, guys, with his spacesuit on.
Jim, while you're exercising, I'd like you to stay intermediate all the time, okay?
There he is standing in the vacuum, guys. Remember, this isn't really even a full vacuum like they would experience on the so-called moon. Or in space, like a spacewalk outside the so-called ISS.
Okay, well, you'll warm up here in a minute, so let's stay right here if you can stand it.
The testing started just normally, like they all do. And Jim was at a vacuum in the spacesuit.
Well, I feel pretty good. Yeah, I'm standing in a vacuum waiting for you guys to just pull it down. I'm sure this suit is going to save me.
With all the air sucked out, all that protected him was his pressurized suit.
Yeah, remember they have to literally put pressure into the suit to counteract the pressure that's not existent around him. Well, obviously there's still pressure around him, but it's very low. So, why do they require the suit to keep the pressure around his body if gravity, guys? I thought gravity is a container. Weird, there's so much containers everywhere.
Then something happened.
I heard over the headset that he was losing suit pressure.
The tube
Ooh, the tube, guys, came loose.
pressurizing his suit had become disconnected.
How did that happen? How did it just come disconnected? He wasn't even moving. Note how he's just standing still in this vacuum, guys. Unlike the guys in the so-called ISS moving around and dancing and going crazy, or even like on the moon playing golf.
He was in serious danger.
There really wasn't any feeling. It was just happening so fast, you know, trying to get the chamber back to a safe pressure and Jim to a safe pressure inside the suit.
As I stumbled backwards, I could feel the saliva on my tongue starting to bubble.
Whew. The saliva on his tongue starting to bubble, guys. Yeah, we see this happen all the time. In a vacuum, fluids tend to bubble and, as they say, boil in a vacuum. Oopsie.
Just
Yeah, this proves you guys Earth space cadets in space very well, guys. Wow.
before I went unconscious. And that's kind of the last thing I remember. Essentially, he had no pressure on the outside of his body, and that's a very unusual case to get. And
very unusual case to get, yeah. Because you require pressure to keep the blood going around in your system. Hey, Derek Nelson, good to see you. I've never seen a Cavendish experiment that was verified to be free from outside influence. So one where it was placed underneath an air duct and where it turned on, the balls moved. Yep. I mean, I've seen the Cavendish show where it goes opposite of what they're showing. I've seen it go where there's no movement at all, and then you see where it goes to it. But like I said, usually when they show it in a air, something with air inside it, what happens when you have two things like this? The air is moving at a faster rate through the smaller duct. So it's creating a lower pressure system, and therefore it can move it together. Do you understand that? So when they place their so-called large ball or mass next to the Cavendish, that's why it moves to it, because you got the low air pressure system. It's just fluid dynamics, guys. That's as simple as that. That's called a party trick. It's the same. Yeah, it's the same as when you hold a when you take a hose pipe and you take the end and you stick your finger on it. You see it squirts further. It's the same, because you're letting it travel through faster because it's got a smaller passage to go through. But this is how these guys actually get these guys to think it's real. That's why when it's done in a vacuum, most of the times you don't get any whatsoever result. I've seen actual null results.
Can I just address wire scuff?
Oh yeah, go ahead.
Because it's not letting me type properly in YouTube. I asked him for DV for Cavendish, so it's put the distance between the masses, which is dependent on the IV or the masses themselves.
This is the same problem all
You
these
need
guys.
to go to school, mate.
This is the same problem all the Globers face when they bring Cavendish as an experiment. They can't give the actual IV for the DV. They can't.
They don't know what
They don't know what it is. Yeah. So yeah, let's go look at some Mr. More things in the vacuum.
4.3 is stable. Next, you would take your O2 actuator IV and then start it.
This is a guy trying to go, and he's gonna practice in a vacuum chamber, guys. So concepts that you created and treat as real. That's about it, Rachie. That's all it is. Another $2 super chat from Facebook. Thank you very much. You really, really are awesome. I really can't thank you enough for your super chat. ISS spacewalk at 17,400 miles per hour filmed. Yeah, I want to see anybody move at that speed outside something in a vacuum and do that with a film. Yeah. And remember, the temperatures outside there is also quite hectic. Oh yeah, before I forget, Fight the Flat Earth asked me if anybody would like to come and debate him on my channel sometime. He's really asking, he's in the mood for a debate. Would any Flat Earth or anybody would like to debate him? Please let me know so I can set up a debate between yourself and Fight the Flat Earth. Obviously, I'll be the moderator, and yeah, it will be on the channel. And I think it'll be interesting to see what would go out. So if you guys really want to debate Fight the Flat Earth, hit me up and I will set it up with you. If you guys do want, we can even set up a tag team kind of debate if you feel necessary that you don't want to debate alone. That is also possible. How about you, Lumpy? Are you in the mood for FTFE?
Yeah, I do it.
You do it?
Yeah, for sure.
Cool. So I'll tell FTFE you in the mood to debate him.
Has he run out of fake flat earthers to debate?
Yeah, anybody can debate him. It doesn't matter. As long as it's on my channel, it's for my content.
Yeah, I'm sorry, but I don't waste your time at all.
He's gonna boil at him.
None of debated you and failed miserably. Why?
Oh, yeah.
What's wrong with the guy?
I don't know.
My opening statement is I predict all his evidence won't actually be evidence.
Yeah, but that's usually the way. Okay, so I'm gonna tell him to we get hold of each other so we can talk and organize a topic and a date and whatever. That'll be awesome.
If we could maintain, point to point and see how it goes.
Yeah, no, we'll have a proper structure, not like, remember when Katz was on here with their so-called unbiased moderator, which was actually very biased. We'll actually
try and do it, claim and then support, refute, then claim, support, refute. We could just go back and forth, claim to claim.
We can do that, yeah.
That way it doesn't get amalgamated into a mess as bad.
Yeah, I think that's a good idea. So yeah, I'm going to let him know you're interested, and then we can organize you guys, talk to each other, and we can figure out the structure and a date and a topic. Okay, you happy with that?
Yeah, I do it. Yeah.
Awesome, thanks, man. I appreciate it. Because he has been hounding me for it, and I said I would ask someone. So, and by the way, he actually contacted me. He wants to see if we can start a channel together. So that's quite interesting. FTF and myself doing it. I don't know what the channel will be about though, but I don't know where I'd get time for it, to be honest.
I'm gonna make it money, but I don't. It is
I
what
don't.
it is. Maybe
I don't mind. I don't mind letting them get money out of it, because I'm being a YouTube creator. I also get money out of it, so I get content as well. So for me, it's fine. I don't bother with that.
No, but they're robbing you of money, because really what should happen is they should all come to your channel, but they're not. They're all going to fight the flat earth.
Yeah, but this would be on my channel, but obviously he's probably going to stream on his channel as well. But it's fine.
You shouldn't allow that. You shouldn't allow that.
Yeah, but it doesn't bother me. Like I said, for me, it's about the content.
If he wants to debate somebody and he wants to go on your channel to do it, it should be your channel only.
Look, when I debate on their channels, I also stream, so I'm not gonna. All good for them if they're making a lot more money off of them. I'm in a much larger channel, so I don't really. To me, it doesn't bother me if they make money off of it, to be honest, because that's what they do. That's their job. So, but everybody for their own, I guess.
Yeah, whatever. I don't know. My hope is that something I say can help. Somebody say this is silly to believe in a water ball and vacuum.
But like we said, there is no actual debate. The globe has died. So at this moment, it's just for entertainment purposes. That's all. Any topic you're going to bring up, how's he going to actually demonstrate it?
Yeah, well, it'll be a correlation or it'll just dodge away. Like some kind of tactic. That's what it always is.
Can you remember when Fight the Flat Earth debated Mitchell? Come on.
Oh, yeah. I don't know if you watched Fight the Flat Earth video he brought out this morning. It was about my debate with Katz. And he started off with my opening statement. And he's supposedly trying to rebut my opening statement. And all he does, he just puts a little short clip of someone just saying, "You say what?" kind of thing. And that's somehow debating me. Debunking what I said on my statements. But anyway, through the whole video, as he's showing what I'm saying, he's literally validating my arguments and showing Katz didn't know what the hell's going on. So it was actually quite funny. But he thinks he's debunking me, but he's validating my arguments. Which is actually funny. Okay, we got 5 minutes and I'm going to have to close off, guys. Oh man, it sucks.
There's a mark on O2 actuator. Alright, stand by.
We can put the sound off because we don't really. It looks like he's standing like he's got an itch or something. But you see how uncomfortable he's standing there. Oh, why do they have to pull him on a pulley, guys? Huh. Yeah, walk back a bit, come on. Spacesuit testing in a vacuum chamber, but why are they testing him with the doors open? That's just another odd thing that I found very interesting. Why do you test it with an open... Oh, there, it's got a glass, so you can't really get that much of a vacuum. So it is closed at least. Just looked like it was open.